there, which I say should work. I did test it, but then I changed it dramatically 5 minutes before the lecture. So maybe it doesn't work. I'm just realizing that might have broken it. But if you go to that, and then it's sort of like, you're not going to
it's okay.
Doing that.
Oh, sorry, I meant this is used. Oh, I think.
You're right. There's Carl Henrik's just having a visitor interest office. So there's the link if you can see it. Do people get that in the chat? Me hosting no, that could go everyone. There you go. Let me change that.
Yeah, I put something that is wrong. Yeah.
There we go.
Yeah, thank you. Do you want to share your notebook or your slides?
Yeah, so I'm going to put the slides on screen, but just people can, if you click on there, let me, I'll show you where you'll get to. He says, I'll just do this portion of the screen. Okay. So you should see a web page like this, which has my slides in it. So you can follow the slides there, but perhaps the thing I'm really talking about is if you want to do the notes and the lab, you can click on Google Colab, and it should bring up a set of notes that also towards the end has a bunch of, all the cells will be hidden, but like using in GPy for emulation. This example I think you'll have seen in well, it used to be one of the lab classes, I'm not sure anymore. And sort of taking you through sort of some of the ideas I'm going to talk about, but using GPy and EmuKit. So that's there. But we'll focus on this one. Resize the screen. You happy for me to start?
I can introduce you.
Yeah.
Thanks everybody for staying at the last session of the summer school. Remember, tomorrow is a workshop, and we are very happy to end the school with the talk by Professor Neil Lawrence, who is actually the founding father of the summer schools, Gaussian process summer schools, I think here and internationally. And so very happy to hear his thoughts about emulation today. Professor Lawrence is the DeepMind professor at the Department of Computer Science and Technology at the University of Cambridge. And he also collaborates in the podcast of Talking Machines. So now up to you, Neil, and thanks for doing this.
Thanks, Maurizio. I should say Maurizio was like a major instigator, because at the time when we started doing these, he was in Colombia and he said, I'll come across and do a series of lectures on Gaussian processes. And that, combined with conversations with Nicolas Durand, who I think you've already heard from, is kind of how I've been wanting to do it for a while, but how we ended up putting the first one together. So I've just lost my, I don't notice I go on fuzzy, so I'm just going to stop and restart video. So put my camera in focus. So today, I mean, one of the great things about watching the series evolve is that I think in the first one I gave in the first one in Colombia I gave all the lectures, but in the first one in Sheffield I gave a lot, and now I don't give very many, because the really nice thing about this and Data Science Africa, which is something Mike Smith has been involved in, is that the sort of attendees from previous schools are often the ones giving the lectures. So almost the entire school is being given now by people who sort of would have been attending earlier schools. So today, I sort of had to come up with a new lecture, that meant, because all the lectures I used to give have been given by other people. And what I thought I'd talk about is emulation, but it's also a sort of sense of, I guess it's one of the things that I myself have learned about more through the schools, through people like Rich Wilkinson, who's here today, and others, and this whole area of using Gaussian processes in this different domain. In fact, sometimes we talk about it as a Gaussian process summer school and an uncertainty quantification summer school. So I just thought I would use this slot to give you my philosophy of emulation and why I think it's such an exciting area to be involved in. And many, probably several of you are already involved and already expert, in which case you'd just be hearing me rabbit on my philosophy. So I often like to start with this quote from Laplace, almost any lecture, whatever it's about. We may regard the present state of the universe as the effect of its past and the cause of its future, An intellect which at a certain moment would know all the forces that set nature in motion and all positions of all items of which nature is composed. If this intellect was also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the teeniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. And this is known as Laplace's Superman, or Laplace's demon sometimes is another name for it. And sometimes Laplace's determinism. And it's a sort of quote reflecting the notion of a deterministic universe that I find very interesting. They're so closely associated with Laplace for reasons we'll see in a minute. But it sort of includes in it three parts. It says, look, if you've got an intellect that's sufficiently vast to submit these data to the analysis, where data is the relative situation of all beings in the universe, and understand all the natural laws, and so intellect being sufficiently vast, I think of that as like, well, can do the computation to merge those things, then it could sort of predict everything. And what I want to just go through with quite a simple example is, you know, why this is a sort of incorrect idea. Not that Laplace was ever incorrect, but we'll come back to that. So, and I'd like to do that through this game called the Game of Life. So the Game of Life is a game that was invented by a vast intellect, and that's John Horton Conway, who's pictured here. And I've sort of chosen a picture I could find of him where he looks somewhat like a god, because he is the god of this game. The game is a cellular automata game, and Conway invented the rules of this automata. And I'm going to tell you what those three rules are. So basically you have a grid, and then in each grid there's pixels which can be either on or off. So here where my mouse is, the pixel's on with the red box around it, and it's surrounded by two other pixels. And there are three rules. So what I'm actually showing you is what's going to happen to the center pixel. Other things might have happened to the outside pixel, but I'm just showing what's going to happen to the center pixel. In each turn, if a pixel is surrounded by two or fewer pixels, then it dies through loneliness. So it dies in the next turn. If a pixel is surrounded by four or more, then it dies through overcrowding. So two ways in which a pixel can die. And if a pixel is surrounded by three, it either stays alive, or if there's no pixel there, a new one is born. So those are the three rules. And what I really like about this is that this is a universe that sits in with the notion that Laplace was talking about, because three very simple rules. They just apply to every pixel in turns. And you've got a game board where you know the situation of all beings in the universe, because you understand the value of all these pixels. You can play this on very large boards. So you have these components that Laplace is talking about that you can predict the future with, which is sort of super interesting. And what I want to show you is, well, even if you know all that, how that pans out in practice. And I want to show you that by sort of using a couple of examples. So within the game, the rules are cleverly designed that you actually get a lot of complexity. So Conway, I think, didn't publish the game until 1970, but one of his friends realized early on that there was a pattern obeying these rules that works in an oscillatory fashion and moves across the image. And this pattern's got the name of glider. So each of these pixels is obeying the rules, but as you go through turns, it moves across. So here we're panning the background, but it would be moving across the plane. So that's pretty cool. That's the sort of complexity you get, and that arises from these rules. What's perhaps more interesting is this pattern, which is a gun that can actually produce these gliders. So you can get this sort of complexity where, and this was sort of, people tried to look for these patterns. So once they had this glider, they were like, oh, can you have a pattern that will produce more than one of these patterns? And so that exists as well. And that took a while to find, but people were actually sort of hunting for that because they like the idea of that. But here's another pattern. This is called the loafer. This is also what's so-called a spaceship. It's an oscillatory pattern that moves. In this case, it moves a bit slower and moves towards the left. And this wasn't discovered until 2013. And what I found interesting about that is the notion that Conway can invent the whole game, and we can specify any board, but that's still not sufficient to tell us all aspects we're interested in for the future. So here, the loafer was unknown to Conway, who's the god of the game. In some sense, he's omniscient in the very real sense about this game, apart from he didn't know about the loafer. And that's, of course, because even in this case where we have access to the whole state of the world and access to exactly the laws that govern that world, that these emergent phenomena that we become interested in, and we become interested in because they can do sort of cool things, we don't have access to. So if I map that to a sort of more real world example, I have a colleague, sort of come collaborator, Neil Robinson, who works at the Met Office, and he does sort of data analytics on their simulation of the climate and weather. And one of the things he told me once that really stuck with me is that he'd just written the code to detect hurricanes. And in order to write the code to detect hurricanes, he had to sort of define what he thought a hurricane was. You know, it's something like, I don't know, the wind speed is above a certain level and it's a certain size, and, you know, it's found in a certain part of the surface of the Earth, I suppose, because I think sometimes they're not hurricanes, are they? They're typhoons if they're in other parts of the world. So he actually had to do something which is effectively what's going on here. We've called this a loafer, and we're defining a loafer as a certain thing, and it's an emergent thing from some simple rules. A hurricane is emerging from sort of whatever we think the rules are, Navier-Stokes equations, plus the positions of particles and plus the sun, whatever else. And we're defining that as an entity, an abstract entity we're interested in. And we want to reason about the number of hurricanes because they cause damage. In the same way in this game, you're interested in reasoning about, you know, the loafers or the gliders because they sort of become the interesting part of the game. And why do they get sort of quite interesting? Because the complexity of this game is such, and I really sort of like this notion, that you can play it. So this is being played, and what we're doing is we're sort of zooming out of the game being played just on an enormously large board. But as you watch this sort of thing here on the white, because this is going to turn out to be I can't remember what they call it. They've got like a megapixel. So people have worked out how to implement these pixels in the game of life. So underneath that, the game of life is operating such that the game of life can simulate itself, which is kind of a bit mind-blowing. And you can go further than that, because it turns out there's a lovely video about it here, that the game of life is Turing complete. You can use these Gaussian guns to sort of create information channels, and you can show that it's Turing complete. And there's a lovely video that describes some of that I've used as inspiration for some of the things I've talked about here. So trying to give you that very simple example of one aspect of this formula that I think underlines not just machine learning, but a lot of what we're trying to do in AI, often in control, and even arguably in statistics, although the emphasis on which terms we care about and how we care about them varies, that we're trying to combine data with a model of the way the world works through computation to make prediction. And these are the elements that are in Laplace's quote, you know, the relative situation of the beings, the natural laws of the universe, an intellect vast enough to submit them to analysis, predict everything, right? So that's the sort of fundamental equation, I think, of what Laplace is talking about. But what I'm trying to show here is even when you have God, so God is Conway, understand data and model, you'll still have this hole where compute is. You still have to wait and explore the space before you know what your universe is going to do, before you know that it's going to produce hurricanes or loafers or whatever else. So that even in this extreme case, uncertainty remains. And that's one of the reasons we love Gaussian processes. And one of the things that really bugs me about people associating that quote with Laplace is, yes, it's a very pithy quote and it sounds very good, but he's using it as a straw man. It's a straw man argument, because one page later, he goes on to say the curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge. Now, this is written in a philosophical essay on probability. So the entire reason for that quote is to sort of be saying, don't be silly. That's not going to happen. And I think you can even see from the case where we get very close to it in a computer simulation, it still doesn't happen. And the reason I find the emulation area so interesting is because in a very real sense, what we're going to do is use the Gaussian process to capture that uncertainty that's there because of, or to sort of speed up our ability to do those computations. So I decided that one reason people really like that quote is because it's got this cool name. It's called Laplace's demon. And I think that biases people towards it, and it's unfortunate. So I've decided that we should start calling this Laplace's gremlin. And Laplace's gremlin, why? Well, gremlins, I don't know if you know about gremlins, but they were sort of little mythical creatures that were only invented, I think, in the sort of First World War or between the wars by airmen who didn't like lack of maintenance on their planes would cause them to crash, but they would often associate that uncertainty about the maintenance in their plane with a gremlin that was actively operating against them. And this is a poster from, they became sort of well known in the Second World War amongst airmen. And this is a sort of poster to sort of remind people to keep things tidy, to sort of do away with the gremlins. So what they're sort of saying here is that gremlins breed in disorder. And gremlins think it's fun to hurt you. So in a very real sense, it's the uncertainty that hurts you. So I'm trying to sort of push that notion that we can think of the uncertainty as Laplace's gremlin, even though gremlins did not exist when Laplace came up with this notion. I mean, they still don't exist today, I think, but you know what I mean. They hadn't been conceived of. Okay, so how does that map to emulation and computation? Well, sorry, it's a bit embarrassing because people like Rich are in the audience. He's much more expert on this than me, but I like listening on the bicycle to Rich telling me about the sort of work he might get up to in climate modeling, where you have this very complex system, which is our planet Earth, and it's often split into models separately. So you might have an ocean model, you might have an atmospheric model, and you might have a land model, and then you might have some model that represents human activity. And you often are trying to combine these models, which are all simulations, very much in the form of Conway's Game of Life, but of course, based on real world physics. But what they choose to do is they select the physics that they find most relevant for their domain. So I'm guessing in the atmosphere, that's mainly Navier-Stokes, but as I say, I'm no expert. But the problem with these things is, of course, that they are very slow to compute. So you get a situation where you're trying to predict either the weather or the climate or whatever, and it takes you a long time. And indeed, the UK's supercomputer, I think, is about to be replaced. But when it was bought, it was like £250 million. The one that's down in Exeter that predicts the weather every day. And these are like the computers that do this are amongst the most powerful computers in the world. But when you look at what we really care about, we might be caring about a question. And so in this case, I'm trying to sort of say, well, actually, we care about temperature rise. And we have these different things, these different models that are coming together and allowing us to answer a question about what will the temperature difference be, if we change human activities in some way, if we allow more so if we encourage the use of electric cars, we might have a model of how humans will respond to that, and then a model of how the atmosphere, the ocean, the land responds to that, and then a model of what the sort of temperature of the future is. Or indeed, we may just be interested locally in what the weather will be like next week, but the idea is the same. But we're sort of faced at the moment with this sort of monolithic system. Well, actually, these things tend to be split up, but monolithic system of these things interacting, and you get this sort of you have to wait a long time to get your answers out. So when you look at systems like this, you find they're pervasive. They're not just around the atmosphere and the what's going on in climate, but I could give you examples of the same type of modeling going on in Amazon for the supply chain. So in the Amazon supply chain, you have models of what demand will be, models of what the supply is going to be like, and then you have models of what your current status of your network is, how you place things. These things just keep coming up everywhere, and they're often based on simulations, simple simulations of the system. And indeed, if it was in supply chain, what we would do is we'd break those models down into separate components. The links here, by the way, are not just the components that interact. It's just a computational graph that we might go through computing the human activities, combine that with the ocean model, combine that with the land model, and then combine that with the atmospheric model, and then make a prediction about temperature once we've got all that information in together. So the real challenge I see with these things, and this is something that we came up with when a lot of the people I was working with, the team I was with, was at Amazon, is what we call the experimental flywheel, is whatever you're doing, whether it's climate or the Amazon supply chain or whatever, when you're looking at experiments And here I'm typically talking about simulation experiments, so it could involve some real world experiments. What you're trying to do is you're trying to accelerate your ability to gain information from the system. And the problem at the moment is that if we're going to build all our experiments with simulations, then this cycle is very slow. We get in this problem that we want to do an experiment, we do the analysis of the experiment, then we design a new experiment, and we go around and around in circles to try and get a better understanding of the system that we're working with. But what we often find is the limiting factor is how quickly this experiment will run, even if it's a simulation because it's going to take many months, or because it's going to require real world data to come in. And when I think about emulation, I think of it as being a very powerful tool for helping us speed up this loop. So this was something we used to say at Amazon, because it's twisting a quote from Jeff Bezos. We don't know what science will want to do in 5 years' time, but we won't want slower experiments, we won't want more expensive experiments, and we won't want a narrower selection of experiments. So the vision that we had there, which leads to a piece of software I'm going to introduce you to in a bit, was that we basically want to speed that loop up. The software we wrote is general, though. It allows everyone else to speed that loop up as well. So we want faster, cheaper, more diverse experiments. Yeah, so that actually became a sort of, I left after 2 years, so, we didn't have to achieve this. I was there for 3 years, but I was only 2 years in that team. So it's clever, always set your goals just outside. So what we were saying is we would like a 2 order of magnitude in the number of experiments we were running on the Amazon supply chain in order to improve it in 3 years' time, which I think was a very achievable aim, actually. And I mean, it was going to be one of those things where it was going to go up a little bit and then breakthrough. I don't know if the breakthrough happened. Actually, what happened, I know the supply chain team has basically just been constantly dealing with COVID and the fact that the whole nature of supply chain has changed pretty much since, well, for the last year. But if we look at, what's available to us in terms of experiments, then this is a sort of map taken from the Met Office. Unfortunately, it's a little bit small. I keep intending to redraw this to get so that it's a bit more readable. But what it shows you is that the Met Office, which, by the way, is an unusual, they have what do they call it, the unified model. They're unusual in that they have a sort of single code base that runs all their different models over different, this is forecast lead times on the x-axis here, and this is spatial scales on the y-axis. So you've got sort of models going up to 300 kilometers on the spatial scale and forecasting out to sort of 100 years time, this model up here. And then you've got other models that are sort of at the 1.5 kilometer spatial scale and forecasting out to sort of about 48 hours. So some of the, down here is weather. And then as we tend to go out here, you're looking at climate. What you'll see, though, is that the gray models are retired. So a number of these models aren't used anymore. So I guess UK4 would have been an old weather model. And when they increased the quality of the supercomputer, I'm just speculating here because I know this vaguely happened, so I think this is true, but I may be wrong in the details, is that they basically got a faster supercomputer and they just increased the resolution of the grid, decreased the sort of spatial length of grid cells, and ran Navier-Stokes over smaller grid cells, getting themselves more accurate forecasts. So you retire the old supercomputer, you can suddenly get more accurate forecasts. Well, you can increase your spatial fidelity. And that is why I kind of really like this plot, because just right on this plot is almost the whole notion of what we might think of as fidelity, because it's not just about one simulation, because when I'm building a simulation, I can optimize the simulation, to be something that is going to be accurate tomorrow or something that's more accurate for 100 years. Well, but maybe it's not accurate for 100 years' time, but in order to make that 100-year times forecast, I end up having to sort of reduce the resolution or increase the sort of size of these grid cells. And those are the sort of models going out over here. Although some of them are pretty impressive, aren't they? 1.5 kilometers. I guess that's a UK only climate model. Again, I'm not sure of the details. There's very likely to be people in the audience here who are experts. So they're all upset with what I'm saying now. So that's what's going on in the simulation world, that you have this ability to sort of access these different types of models and speed things up that way. So I'm trying to represent that here in a little diagram where this is a sort of high fidelity simulator and these are 2 low fidelity simulators. And then I'm arguing that we also have some access to the real world. Now in climate, that access to the real world is typically retrospective, but there are other areas where this type of setup is used, like Formula One strategy modeling, or even Formula One aerodynamics modeling, where real world might be, not fully real world. It might be testing in a wind tunnel, or it might be testing in a track. So there are worlds where you get to combine these things, and certainly Amazon supply chain, you get to combine these things, because real world would be, okay, test your idea on some subset of products. So change the business logic behind how you're operating with some subset of your products and do an A/B test on performance. But the point is, the real world experiment, that experiment might take many months to complete, and it's expensive. And you've got simple simulations that give you a sense of whether this is directionally right, and more higher fidelity, slower simulations. And what emulation can really do for us here, and here, when I say emulation, for the purposes of this meeting, we can just think Gaussian processes. There are other approaches you can use. And indeed, we have horror of horrors, deployed a neural network emulator within Amazon that I think runs every time you click an Amazon web page for a product. So yes, we have used, and the reason we did that is because uncertainty wasn't an issue. It was all about training the emulator on large amounts of data. So yes, you can use other things, but just for the purposes of today, think about a Gaussian process as your emulator. And what your emulator is going to do is it's going to, instead of trying to reconstruct the whole simulation, it's just going to say, well, what were the inputs to the simulator? So which might be the initial conditions. And what's the output I care about, which might be the temperature in 100 years' time or whatever, and try and build a regression function between those two. And the notion here is that you build that emulator so that instead of having to go back and rerun the simulator every time you want to query those inputs, you just run the emulator instead. And what I really like about this is, without a statistical emulator of this type, what you get is an inability to sort of unify simulations and the real world. Because one of the things you can now do with these emulators is you can do what we might think of, this strictly speaking isn't multi-fidelity emulation, but you can build emulators that sort of try and also model the difference between the simulator and what you see in the real world. So you're building a model that has a sense of when it's going to be wrong. Now, if you're properly handling the uncertainty in this model, what that will give you is an ability to sort of say, well, I can run the simulator now, but if I run it in a regime where I know it's not well calibrated to the real world, I might have more uncertainty than if I run it in a regime where it's well calibrated to the real world. And then the multi-fidelity emulation trick is that actually, yes, you have an emulator that will look at multiple different types of simulator. So in my head, I mean, a good example of this would be, I think sometimes of wind tunnel in Formula One as really as a form of simulator. And what you might have is computational fluid dynamics models of the aerodynamics of a Formula One car, and there's different models you can use which have different strengths and weaknesses. I think very often how they deal with turbulence differs. So you might have a couple of those, and then you might have the ability to put the car in the wind tunnel, and then every couple of weeks you get to do a little bit of testing on the track. I mean, they get to do very little testing, which is why this cycle becomes so important for them. And they can interrelate the different parts of the car. And we've had actually several Formula One teams come through the course. And they rarely tell us exactly what they're working on, but I strongly suspect some of them work on this type of thing because it's quite common practice in not just Formula One, but we also did similar things with Primaire when we were in Amazon. And Primaire people attended this course, learn how to do that. So that's a really, really useful thing. The other thing I should say is, in my head, there's never think that there's one emulator to rule them all. For me, the clever point about this is you can actually store the data from these simulations, and you will want to use different emulators for answering different questions in different contexts. And the most extreme version of this is, I would tend to think that a lot of the interpretability work that's going on at the moment, where people are linearizing around the outputs of a neural network, if you're familiar with that, you could view that as emulation, right? Because the linear model is giving you an interpretable model. And indeed, in supply chain, that came up an enormous amount, a technique known as bridging, where vice presidents wanted to know why the stock was low. The very common approach to answer that question was to linearize around an operating point and give an answer that was based on that linearization so that you got an interpretable answer. And I would see that as a form of emulation as well, although people might argue that. So then obviously you need an emulator every time they ask a question. And I think that's not going to be an uncommon scenario. So what I want to tell you about now a little bit is this framework that, I mean, I'll include everyone who's in it, but Javier Gonzalez, who came to me, well, was postdoc with us in Sheffield, but went to Amazon with me, and then he led a team that was doing this inside Amazon. So the projects I basically told you about were all being led by Javier. He's at Microsoft Research now. He probably lectured this summer school. He often does, and he often does I know he didn't do the Bayesian optimization this time, but he often does you may have seen videos of him doing that. So what we decided was that with this being a very important framework, and we'd written GPyOpt, which is a Bayesian optimization framework, and that was quite popular, quite successful, but it gave us thought around, well, if we care about emulation, then we just see Bayesian optimization as an example of emulation. Why is that? Because if you think about what's going on in Bayesian optimization, you're emulating the function you're trying to minimize. So you can see that when you have this Gaussian process plus an acquisition function, the acquisition function is helping you decide where to acquire points next, but that's really that's associated with what you're trying to do, which is to minimize the function. If you weren't trying to minimize the function, you would just have a different acquisition function. So let's say that you were trying to find out how to make your car faster, so that you're well, then you can have a very complex minimization function around, I'm going to minimize the drag on this car. In fact, in practice, they don't do it that way because that tends to find corner cases. But, for these different tasks, you would end up with different types of acquisition function. And that's the kind of philosophy EmuKit builds on. So a lot of the lab is sort of inducing you into EmuKit. And what I'm going to do is just give you sort of an overview of what it can do here, and then probably go for questions and let you play with it a bit more in the lab. So just to give you that sense, so this is the EmuKit webpage that if you go to, it's also linked in the notes, you'll see that it's got these different examples of these different tasks you can do. There's the playground. The playground is set up because we wanted to sort of explain to managers what we were doing, because a big project like this always needs funding. So the playground was very much helping sort of vice presidents who are funding us understand, get an intuition for what emulation was. And so it's got a sort of taxi example in there. You can do Bayesian optimization on that, and it's all done in JavaScript. Then it's got different examples. Bayesian optimization, you've seen multi-fidelity emulation, which is what I was just talking about. Experiment design, so where should you acquire data points? That's key. Bayesian quadrature, so when you are trying to solve an integral across a sort of simulation, you can effectively do that with quadrature. And sensitivity analysis, so trying to understand within your simulation which of the inputs are really the ones that are controlling the output. So that also helps with interpretability. So it's got a bunch of examples in that way, but it's also a general framework. So this is the sort of team. And what I really like about this team is all of them have been through the Gaussian process summer school. And it's, we actually, within Amazon, it wasn't very into open source software, but we persuaded them to release this open source, and it was released open source by Amazon, but it's actually now managed by Andre, who's here, and sort of freely available, BSD licensed. But I think that the project really reflects the philosophy of the school, which is that we're trying to share knowledge and bring people together who have that knowledge to further share that knowledge and make things easier to do. And therefore you end up with a highly collaborative project where I think probably Maren was at the first GPSS we did. Mark joined us, Mark and Andre joined us at Amazon and came once they were already working for Amazon. Mark now works for, I think it's called Arrival, which is an electric van firm based in London. So that's the sort of team, also with Aaron Klein, who was an intern with us, Alex Gesno, who was an intern with us, Henry Moss and David Elias Kunzel, all were people who were working on it at Amazon as interns. And Cliff was the software engineering manager. I also did management. So I got to that point where, I had meetings and then this happened, which is how, that's how I live my life. I'm not sure that it was any causal that the meetings I had caused this to happen, but because really Javier did it, but I claim management in this case. You'll see I haven't checked in any code. The whole point about EmuKit is to give a modular design to solving these sort of problems. So here, for example, and we're very clear, although of course we love GPy because we sort of made GPy, and indeed GPy grew through this school. So the whole idea was we'll make GPy, we'll have a common Gaussian process framework, and people will be able to use it and improve it. And now there's like 5 Gaussian process frameworks, so that hasn't really worked. But I mean, GPy does, I think, is a nice framework. I mean, I guess one issue, it doesn't have automatic differentiation, which a lot of new frameworks does, but it's a very user-friendly framework for people who want to construct Gaussian processes. But we didn't want to sort of have a emulation framework that sort of said you have to use GPy. So the first thing you have is model wrappers. So whatever you're going to use as your emulation model, you just have to wrap it. You have to write a very simple wrapper. You could use what are they? GP Flow, you could use GPyTorch, you could use anything. I mean, it's in Python. Okay, so you're restricted in Python. What's the new one? GP Flux. And of course, what you're going to use is going to depend on what you're doing. And there's a notebook there you can click through to on how to build your own model, and you can sort of wrap your own model in the way you like there. So that modular functionality goes through to the structure that you basically have. You have a loop that is going to iterate around the acquisition. It's almost like a mini version of that experiment analyze design loop. You've got candidate point calculator, you've got the acquisition function, you've got the optimization, the acquisition function to find that point, and you've got the user function that you're trying to operate against, your model updater, so you've got a new point, and then you have your stopping criterion. So by splitting it up into these components, then we end up with a very flexible framework that can do Bayesian optimization, a bunch of other stuff. You know, of course, at some point you find, oh, I can't do this particular task, and then you have to think again, and that's why you end up with new frameworks. But for the moment, I think this is about the most general thing going. So the vision behind it is that you have those models, you're combining them with model interfaces to these methods that might be Bayesian optimization or quadrature or experimental design. And in the long term, we've always had this notion of tasks where you get a number of these things together to solve a problem, because part of the notion here is that there's no point. The reason you bring uncertainty in, I mean, we all like uncertainty, I presume, because we're at the Gaussian process summer school, unless it's like a spy in the audience. But I think one thing that I've noticed the community gets wrong is uncertainty is not there for uncertainty's sake, right? We get so into it and trying to persuade people they should have it that people sort of, they never answer the question why. And the truth is that the why comes when you choose to make a decision, right? When you choose to collapse your uncertainty and make a decision. Sustaining the uncertainty is good, but it's actually about the decision. And you sort of see that in Bayesian optimization. So I think Bayesian optimization is a really interesting formalism because you're never going to be 100% well calibrated on your uncertainties. But by using Bayesian optimization, you can test some different models that have different strengths and weaknesses in terms of how they scale or whatever else they're doing around representing uncertainty. And you can see what works in practice to minimize the function you care about. That's a really important notion to me. I think it's kind of pointless to say which is the best model if you haven't defined what the task is at the end of the day. And so that's kind of a notion that's there in EmuKit, although not as developed as it could be. So I think I've probably said most of these things. So high-level tasks are high-level goals that owners of the process simulator might be actually interested in. Measure the quality of the simulator, explain complex system behavior. You see, because we need to move away from the, oh, I did this optimization, make the car faster. You want to compose these different things together to try and get that answer out. Okay. I think looking at the time, I don't want to talk about the details of those parts. You can sort of read them there if you want to play with the playground. So if you have, and I hope some of you are in this position because we always have such a nice diverse audience. If you have a manager you're trying to explain these concepts to, then EmuKit Playground is potentially your starting point. So Adam Hurst was a sort of software engineering intern. I think that might work for Amazon because he came back. He was really good. And he worked with Cliff and they built this sort of little emulation that works in the web browser and a tutorial on emulation, which I think turns out to be really important when you're trying to explain to people why this is an interesting thing to do. Showing them a Gaussian process equation, update equation doesn't normally help. So that's a sort of image of that. And then online, what you'll see is there's a tutorial in terms of the how you use EmuKit. You'll be able to go through examples of these things. You'll see that's in the notes that I provided you on the Colab. In fact, why don't I switch to that now as I wrap up? So what you see is, first of all, the notion of emulation is being covered. This is in GPy, and this is an example that actually Nicolas Durand wrote for the first Gaussian process summer school that I borrowed here for sort of doing emulation of this function and working out what the mean of the function is using a Gaussian process. And there's a sort of some questions there you can have a go answering. That's without using EmuKit. And then you'll get this introduction to EmuKit. So this should install the relevant parts. All these install commands get the code into Colab so that it's working for you. This should work out of the box on Colab. And there's a little preface sort of overviewing some of the things I've just said. And then you start going into a tutorial. So this is the first tutorial for EmuKit. And if you run through that, it'll start showing you the translation of what I'm talking about in practice, right? So this is, you're doing some acquisition on just emulating a sine function, obviously not that exciting. The tutorial then goes into a section on sensitivity analysis. I should say a lot of the stuff that I'm sharing with you here was written by Javier, Mara, and others as part of the EmuKit tutorial. I just put them together for you to do in one place for this. So you can just go to those tutorials if you prefer. And then at the end, you've got sort of sensitivity analysis test that you can look at doing. And then my favorite bit is, and this is from Nicolas, who wrote this catapult simulator. So the final thing it asks you to do is do a sensitivity analysis on this little simulator that Nicolas has written. So what you have to do is you start this simulator and then you do a sensitivity analysis on the simulator using experimental design to acquire the relevant points for the sensitivity analysis. Now, one word of warning, if you do go as far as doing that, this final stage, for some reason, is very, it does say where, is very slow in the Colab. So this final thing that you get asked to do at the end of the notebook is much faster on a machine locally than in Colab. In Colab, each of the update iterations where the model's doing the acquisition for the next point seems to take 50 seconds for some reason, whereas on a local machine, it's just extremely fast. I don't quite know why that is. With that, I'm going to sort of stop there and see if there are questions for the sort of last 15 minutes. So just to summarize, what I've tried to do is motivate through the sort of notion of Laplace's demon, but Laplace's gremlin is the thing I want you to remember now. Just forget Laplace's demon. This is why it's so important. When someone mentions Laplace's demon, you can say, but do you know about Laplace's gremlin? Because then we can get rid of this world where people associate Laplace with determinism, because that's highly inaccurate. And sort of explain that, even in the world where we understand the whole of the physics, we still are left with this, and where everything is, this problem of uncertainty that's coming from computation. And then what I've been motivating is this field of emulation, or it would also be called uncertainty quantification or surrogate modeling, as an answer to that problem of uncertainty in the computation, to speeding that up so that we can loop through these experiments and focus our interest on the right areas to answer the question we care about. And EmuKit is a software framework that is designed to enable that. The notion being that you express the thing you care about in a task, and that's got these subtasks, which are experimental design and sensitivity analysis, like we've got here for the catapult. And I'll stop sharing there and see if there are any questions.
Cool, yeah, feel free to ask, sorry, I've got a mic here. Hey, feel free to ask any questions if you have any, and if anyone wants to post a question, just either write it in the chat and we'll unmute you and go ahead. Yep.
Rich will have a question if none of you have questions.
Yeah.
Because he'll object to something I've said, if he's still there, yeah.
Yeah, he's still there.
I've just heard my name. I've gone into a panic. What are you talking about?
So you probably drifted off after 5 minutes. I was just saying that you'd have a question if no one else had a question, because I said some.
What are you talking about?
Pardon? Who's this Laplace guy? Yeah, I always talk about Laplace. Rich knows why I talk about Laplace, because if I talk about Laplace, I can eliminate all of statistics and just claim that machine learning stems from Laplace and never have to mention statisticians at all. And he really likes it when I do that.
Give me a moment, I'll think of a question.
There we go. I suppose the notebooks in the GitHub EmuKit project are demonstrating all aspects of the tool. Yeah. I mean, if you can go through those notebooks just as well. My ones try and put it in a context of why we're doing this and what the motivation is. Yeah. So Harry's got a question. Do you want to ask your question live, Harry?
Yourself?
Yeah. Is he able to do that? I can just read out Harry's question. How do you do it, Mike? Do you prefer?
Hang on a sec.
I can answer Rich's question in the meantime.
I can't actually unmute his microphone probably.
Okay, right. So I'll just read out his question. Harry's got a question. It would be amazing to have a resource of references to more general leading like Laplace's essay and probability. Would it be possible for the summer school to organize this? Yeah, I guess. I mean, in some sense, it's just the stuff you'll see in the lectures. But yeah, we should collate them somehow and put a reading list. I'm not sure you should read the whole essay on probability. It's something that I did because when I realized it said that on page 5 and everyone else seemed to have stopped reading on page 4, I thought I'd better read the whole thing. There is other stuff in there, like about there's some Petersburg paradox and logarithms, but he's getting that from Bernoulli, I think, isn't he? Not so. It's interesting the extent to which things he says in there, I think you can trace to Bernoulli, but he was a big student of Bernoulli's. Have you tried emulating the game of life is a question from Rich. I think that's so interesting. So it's like the sort of thing I want to set as a student project, or would like to if someone was interested, because I suspect it's pretty difficult to emulate, right? I don't know. I mean, I find that why do I find it very interesting? Because I think that there's a notion in there that we don't really capture in a lot of what we're doing in modeling, which is what is the object of interest? We rely on human experts to tell us that like it's a hurricane, or it's a forest, or it's this ocean, or it's this area of an ocean, or a continent exists. And, the game of life gives you this opportunity potentially to really look at that abstraction process, like what is the object of interest? Like we have defined them all. They call them spaceships or oscillating patterns. So maybe it's maybe it's not as interesting as I'm making out, but there's probably things you can do there. Raina has a question with hand up.
Yeah, I've tried to unmute. Feel free to unmute yourself to ask the question if you.
I think, Raina, you should be able to unmute yourself because you're in the panel.
Maybe they've disappeared. I don't know.
Let me try unmuting. Let's see how powerful I am.
I suspect.
Asked to unmute. I can click the button, but it doesn't seem to have an effect. Raina, do you want to, if you had a question with your hand up, do you want to put it in the chat? Or
am I allowed to ask a question?
Yeah, of course.
It's all like, I always worry still about the and like, I don't know, maybe it's the last few days, people keep talking about Bayesian optimization. For me, it was a problem on the sensor placement of the air pollution sensors, right, in Kampala. And they've been spread out evenly over the city, which kind of makes sense, right, from the point of view of wanting to, like, if you have but there's these spikes. Okay, this is actually the problem I'm currently like discussing with someone today. There's these spikes in all of the sensors, and they seem like they're real pollution spikes, but they never appear in more than one sensor. Like the sensor 800 meters away doesn't see the spike. So they probably are, we're fairly sure they're real pollution, but they're fairly local. If only we put them close together, then we would know what the length scale is of the
yeah. So if
like,
you look at the design of experiments code, then it will do that. So you can look, if you do the, you should see what you needed to have done is the design of experiments lab in EmuKit. And what you'll see is that there are different, I mean, there's like Latin hypercube, but there's these different approaches. And one approach is that, it's only optimal to spread them evenly apart if you have a really deterministic understanding of the length scale. So Gaussian processes will often tell you to do that if you do experimental design with a fixed length scale, right? But if you start doing things where you're uncertain of what the length scale is, then all of a sudden the model's like, no, I also need some points really close together because I need to explore the length scale, right? And so that sense that we have that they should be equally spaced is a sense that's emerging. And your question is exactly a length scale question. Is that spike real or is it noise? And you can't see that unless you've got a second sensor quite close. So you have to be careful because there are parts of the uncertainty that the Gaussian process is not naturally handling for you unless you start doing sampling. And you can get lulled into this sense of security about what you're doing by overly relying on the Gaussian process and forgetting its weaknesses.
Yeah. So there is a sensor on top of it, like there's two sensors in the same place. We are literally in the same place. So that doesn't give.
Well, that's for noise detection. That's when you're assuming that the length scale is so small that it's indistinguishable. Well, they can't be literally at the same place, like because of quantum supposition theories or something.
5 centimeters apart, you know what I mean? It's
yeah, so it's still a length scale. I mean, there's an assumption there, isn't there, already?
yeah, that's true. Yeah, we are bringing an assumption.
Does Emukit work with deep GPs to decrease computational time compared to GPs? So what's DGPs, Madji, here? Could you just maybe put in the chat? Does Emukit work with DGPs? I'm thinking deep Gaussian processes. Okay. No. Yeah, so I think if I understand what you're saying, Emukit does work with deep GPs. So one thing you can do is one thing I love deep GPs for, and we've done a little bit of, and other people have done too, is multi-fidelity emulation. So you model the relationship between these different fidelities of simulation and the real world with a composition of Gaussian processes. Yeah. So that's a really nice trick. So in that sense, you can use Emukit with deep GPs. But I think you're not asking that. I think you're asking, can we solve challenges of larger computational time in deep GPs with emulation? And yeah, no, you can't really, no, because it's not, I don't know. It's an interesting point. I suppose, that's what Bayesian optimization for hyperparameter optimization is doing. Yeah. So you can at that level, but not in terms of like dealing with the fact that your linear algebra is problematic, because you actually need to solve that linear system to fit the, but I may have understood.
Can you hear me?
Oh, yeah, we can hear you. Brilliant.
Okay, like for my problem, for my research, like I'm doing an emulation, in fact, for a complex computational problem and climate modeling, in fact. So could we use like the deep Gaussian processes instead of the Gaussian process for such like general problems?
Absolutely. It's a great question. People have started doing it and it works. There's definitely demos out there using Emukit to do that.
Okay.
I think it's a really good thing to do for a few reasons. Because you can get sort of like the problem that Mike was just talking about in terms of the not knowing the length scale and whatever else. In some sense, you can see, well, what a deep GP is doing is you can almost see it as well. It's a non-parametric warping on a GP. So it actually introduces uncertainty over that. So a deep GP doesn't have a sense, even if it's the stationary covariance functions two put together, it doesn't have a sense of, oh, there's one fixed length scale. So it will sort of handle these dynamic changes in length scale. And it also can handle sort of quite unusual uncertainties. The negative thing about it, of course, is that we can't compute them analytically. So there's always some approximation to how you're doing your uncertainty. And the general one people are using is assuming independence across layers of the GP to get the posterior tractable. And that means that somehow you're not capturing the uncertainty absolutely perfectly. So you end up back in this position of, I've got a more complex model, but I'm not capturing the uncertainty absolutely. So, it's one of those things, the proof of the pudding is in the eating. You still have to run the whole process to see if it worked better. You can't guarantee it's going to work better. But in the cases we've used it, which included with the Prime-Air drones, we use deep Gaussian processes to get them flying. And other cases, it's worked really, really well. So yeah, I think it's a great idea and well worth pursuing.
I just have a second question. Does deep GP work with multiple outputs?
Yeah, absolutely. So in fact, the first deep GPs we built we were doing unsupervised learning with very high dimensional outputs. So just like if you've studied the GPLVM, you can think of a deep GP as like a GPLVM with a Gaussian process on as the prior, right? And in those cases, you can be looking at millions of outputs. Of course, there's some constraints about if you want to use a different covariance function for each output in the final layer GP, that affects your computation. But yes, in general, it does. And I think that can often be a very interesting use case to build a model for that.
Great, thanks.
Anonymous attendee asks, broad question, what's the current bottleneck for deep GPs and what do you think will solve it? It's a great question, anonymous attendee. I think it partially depends on which domain you're wanting to deploy them in. I've thought for a number of years now that the main obstacle is lack of the equivalent software of GPy. Now, what do I mean by that? I don't think we've got the right Gaussian process software yet. I haven't used all the other frameworks, but the situation we're in is, I think GPy, when I talk to people, it's very widely used. People like it because it's intuitive for the user who's trying to construct covariance functions based on their knowledge of the world. And it is indeed targeted at that. But it's less easy to use, perhaps, if you want to create a new deep Gaussian process algorithm, because it doesn't, if you look at things like TensorFlow and PyTorch and these things and the way they compose things together, it doesn't make it so easy to compose things together. And if you do start composing things together in that way, where frameworks have allowed you to do that, like, I guess, I don't know which frameworks are, some frameworks, I mean, there's sort of in these frameworks to some extent, they don't give you the sort of ease of functionality of use that GPy gives in terms of your interface, like in terms of what you're building. So I think so I kind of do think it's software, and I don't just mean like we need a new software package. Lots of people keep writing new software packages. In fact, that's one frustration I have with it, because they write them sort of somewhat on their own with their imagined idea of what problem people are trying to solve. And that means they rarely bridge this gap between a software that gives you the flexibility to construct something. I mean, workshop tomorrow is all about software. It gives you the flexibility to construct something novel which is like composed of different Gaussian processes, but also looks good from the user side, the domain expert side. That's a really difficult thing to bridge. And a lot of these packages are written by people who haven't spent that much time deploying these things, so they don't know both of these worlds. I mean, I don't think it's algorithmic. I mean, you could say, well, it's the computation. Well, no, because we know that the stochastic variational inference works, but what we don't have is what they have in, say, sort of neural networks now, which is 25,000 people trying their latest idea on how to make it work better. I mean, most of the progress in neural networks, to be frank, is the sort of how many monkeys is it trying to type Shakespeare? I mean, they're not monkeys, but it's that effect. It's that effect of if you have 15,000 people trying things, some of them are going to get something right, and we just don't have that going on at that scale at the moment. So we're much closer to, say, the way the neural networks community was in, say, the 1990s, where relatively few people were trying things, although we've got better computation. So I've basically thought since 2000 and whatever, since Andreas did the work, that, oh, fantastic, this is going to solve a lot of problems. And I've not really worried about it since then, because I've just thought that over time, if I was right, it would be proved to be true. And I think we're sort of seeing that now. Potentially, like this new framework, GP Flux, is going to do something. I'm working with a student called Vidi, who's actually really a student of Carl Rasmussen's, who's just deployed stochastic variational inference and GPLVMs in PyTorch as a sort of stand thing, or GPyTorch, or whichever one. And I guess that's going to happen more and more. And I think as that happens more and more, we'll start converging around things that are more useful. Another question here, which is, can you explain further the interest of deep GPs in comparison to simple GP for multi-fidelity emulation? Mehdi, you can unmute and sort of follow up on that if you want. Mehdi.
Yeah, can you hear me?
Yeah.
Okay, good. Yeah, I'm working on multi-fidelity data fusion with what you said before, wind tunnel and CFD simulation. So I'm interested in your opinion on that, particularly on.
Well, there's a good
the
notebook on it. The Multifidelity notebook will basically take you through about the depth of my knowledge on it. But you know, the multi-fidelity GPs that people use are, if you just use a standard GP, you're effectively making assumptions about linearity between the two functions you care about. So you're sort of assuming that the you know, that there's some linear sum of functions involved, because the linear sum of two Gaussian processes is another Gaussian process. So what you're saying is something like, well, the real world is, I can't remember which way around is the correct way to say it, but it would be some sort of statement like, I'm going to model the real world as the simulation plus a Gaussian process. So the discrepancy between the real world and my simulation is a GP. But very often that won't be the case. And I think, I suspect aerodynamics is one thing where it isn't the case, because where discrepancies occur, they'll tend to occur, I think, and you'll know more about this than me, Mehdi, but around where you get to break into turbulence and that sort of effect. And that will tend to be occurring in quite a non-linear way in the simulation versus the real world. I don't know, is that right, Mehdi? Would that make sense?
Yeah, exactly, yeah.
Yeah, so in that case,
and turbulence.
Yeah, I mean, we had this paper with Paris Pericardis and Andreas and others, which I think is one of the first on this type of multi-fidelity emulation, where you say, well, actually, I'm going to compose the functions. You know, linear composition is like addition, but now I'm going to say, well, what I observe is a function of a nonlinear function of the previous function, and now immediately I've got a deep Gaussian process. Yeah, but one where I'm seeing observations potentially in one of the what would be hidden layers. And that's the basic idea. And of course, it's quite general, because you could also use a deep Gaussian process for emulation in the base case, right? You could just use, so, you know, you might want to model the simulator with a deep Gaussian process, first of all, and then the real world with a difference between those two is another deep Gaussian process. But once I can compose Gaussian processes, I can do whatever I like there. The problem becomes that people haven't written software frameworks that makes it easy for me to say that, and you to go away and go, great, I'm just going to piece that together and see what happens. You know, you have to be quite expert in how to manipulate the existing software in order to get that going. And that's why I think that that's the bottleneck. Does that make sense?
Yeah, definitely. Thanks.
Cool.
Are you in aerospace, Mehdi, or are you in Formula One?
Aerospace, yeah.
Aerospace. Well, the nice thing in aerospace is the cycle times are a lot longer than Formula One. I mean, it's almost like the really interesting thing about Formula One is when they're setting up those things, maybe people in the audience know better than me, you're trying to cycle that, do that iteration cycle really, really, really quickly. And that was a massive inspiration for us in Amazon in going around and saying to people, you need to turn this cycle around much, much quicker, because, you know, then you get more experiments, you get more information, you can probably design something better. That was our notion at any rate.
Cool, I think we're out of time. And I don't know if, I think everyone's exhausted by 3 days of Gaussian processes, maybe, I don't know. But anyway, yeah, thanks, Neil. That's like really interesting. Yeah, it's good to see like each year how your ideas sort of like progress and change and like draw more things in.
I just try and each year try and say something different now, because everyone else, like now we've trained everyone, they all know this stuff already. So
that's true. Right. Yeah, thanks again. So tomorrow is the sort of workshop day where we're looking at software. So this is probably, and I think, I mean, deep things are mentioned. I haven't actually checked to see if that was deep GPs being mentioned for tomorrow. I'm sure they've come up. So I won't go through the details, but anyone can look at the web page. So that starts at about 9 o'clock with Zenwen. So you've heard him speak already, so he'll be talking more specifically about implementations. So yeah, I look forward to seeing everyone there. Mauricio, do you have anything to add?
No, just thanks for the talk. You need to talk about. I think you're doing every time you do meta GP, so meta learning, something meta.
Don't tell anyone, that's my only trick. Every time people do things, go meta.
Really nice. Okay. Thanks everybody, and yeah, I hope you can join us tomorrow for the workshop as well. Yeah, see you tomorrow.
Take care,
Everyone, thanks. Ciao, ciao.